Okay, hello everyone. Welcome to lecture number 9 in ECE 576. Before we get started, as always, if you have questions or comments, let me know. Okay, so a few announcements before we get started. One thing is about the projects, course projects. So the project mid-review report has been uploaded as an assignment. It is ungraded and requires submission of a half-baked report of the project. So it serves two purposes. One is that you get feedback timely to improve your projects, and also to understand whether your progress is in line with the expectations. And also for me to understand if you need help or if you are on the right track. So please make sure you can submit as much information in the project mid-review report. There is no format. Just try to be as close as possible to what you're eventually considering to submit. And this one is due on March 31. Okay, so after this, you will have a project presentation. So that will be the week of April. So it's 1 week before your final exams. So April 21, you will have project presentations. So in class or for people who cannot attend, they can submit a recorded presentation. Okay, so that week we will not have a regular lecture, but instead we will have a list of presentations so everybody can see what other people are doing. You can ask questions, and you will have a 10-minute slot for every group. So I will say a 10-minute time slot. Okay, and once we reach closer to the deadline, I will set up a schedule for people to present. So I will allocate time slots to groups so that they can share their screens and do a quick 10-minute presentation. If you want to do recorded video, then again, same format, 10 minutes. I'm going to post that to the whole class. So it's up to you. You can pick which option you want. And this is part of your, a small part of your grade in the project. And the last thing is the project report submission. So after we get done with the project presentation, you will still have a week to prepare your final project reports. So that's going to be due April 28, end of the day. And once you submit your final project reports, then we will move towards the grades, because this course does not have a final exam. So your grade largely depends on your project and the graded assessments. All right, any questions before we get to the technical part? All right, if not, then um, I'm going to pick it up from our last lecture, and we will have some miscellaneous discussions, right? So some topics that were missed in our previous lectures, and some things that are important to talk about before we can switch our topic to the next one. So some assorted discussions. The first one is about the order of controllers and observers, right? So when we say full order observer, full order controller, what do we mean by that? I mean, it's important to clarify. I think implicitly people know this, but we haven't really clarified what does it mean by having a full order controller or a full order observer. So full order basically mean that all the states are involved. So so if you're saying a full order controller, then what you mean is that all your x, which is the state vector, are involved in the controller design. Otherwise, if it's a reduced order observer, that then it means that a subset of the states are actually part of the controller. So all the states are used in the feedback. U equals 2 minus kx. So this k really is, sorry, this x is the vector of states, right? However, if it's a reduced order observer, then by decomposing the system into controllable and uncontrollable parts, you can have x1 and x2, or x controllable as the subcomponent of the state vector, and a controller designed using that sub state vector is called a reduced order controller. So similarly, a full order observer again implies that that all the states are being estimated. So when this does not happen, then there's something called partial state feedback. So that means you've actually decomposed your system. So your original system, which may have controllable and uncontrollable parts, you've decomposed it into those subsystems. So into controllable and uncontrollable parts. And then we design controller only for the controller parts, or only for the controllable parts. In other words, when we say x dot is ax plus bu, you will decompose it into x controllable dot equals to a controllable x controllable plus b controllable u, and then your controller u equals to minus k x controllable. So this k will be, or this u will be a partial state feedback. Okay. Now, so this is partial state feedback, but the analogous idea in the observer case is called a reduced order observer. So the meaning is quite similar. It says that you construct a system or a subsystem of states. So that subsystem involves states that are not completely visible at the output. And then we design the estimator only for those states. So for example, let's say if y equals to x in the control in the control system, then we actually do not need to do any estimator, right? Because all the states are fully observable at the output. So we can directly use that into the feedback loop. So we do not need any estimator for x. Okay, so, and let's say if it's not completely observed at the output, and instead let's say there is only y equals to x1, and in that case you will not need an estimate for x1, but you have to have estimates for x2 and x3, right? So instead you will need estimators for the states x2 and x3, right? Assuming 3 states system, and so on, right? So therefore, if that's the case, we will we decompose the original system. Excluding x1, and then create an observer to estimate x or the remaining states. Okay, so I'm sure we have dealt with this idea before. but just stating it more formally because we are now going to move on to next topics. So we are not going to come back to observers and state feedback controllers. So trying to wrap the discussion here. Another thing I just want to again reiterate is the idea of internal and external stability. So we have talked about stability of LTI systems, and mainly in the context of bounded input, bounded output stability. But there's also something called internal and external stability. Maybe we have had references to these, but just trying to state more formally here. So internal stability means or is related to the behavior of the system when the input is 0. So it is related to the, let's say, the 0 input response. Meaning that if you don't consider the input to the system, just considering x dot equals to ax, right, where there is no input, right, no input u, and whether this system is stable or not, right? And if you remember, you know, we said x of t is actually x at t0, which is the initial condition, and then e raised to the power alpha 1 t plus so on, right? So this exponential, you know, this is the critical element because the initial condition is always a finite condition. So what is implied here is that system is stable as long as these terms do not blow up. Right? And this term will blow up only based on what is the alpha, right? So alpha is a whole location. So alpha 1, alpha 2, and so on. We have these poles, and these appear in the exponents of the exponential. So as long as these exponents are negative, your 0 input response decays to 0 eventually, and the system is stable. It does not blow up. So the key results here, which you've seen previously, is that the system is marginally stable if every initial state generates a bounded X response. Right, so bounded it's a 0 input response. Right, so no matter what the output, the input is, because input does not matter in this 0 input response. So if as long as the every initial state can lead to a bounded response, then the system is marginally stable. Now, it is asymptotically stable if in addition x of t goes to 0 as t goes to infinity. So, I mean, these are two different stability ideas. So if I can draw here, let's say the 0 input response looks like, so let's say it starts, I mean, if you, for some x0, if the 0 input response, let's say is the following, then this is a marginally stable system. Right, so if this is the case, then it's marginally stable because the 0 input response is bounded, right? It's always, it's not going to infinity, but it's always within bounds. But in the case of asymptotically stable, let's say the response is like this, then this is a asymptotically stable system, because there is this added condition that the response has to decay down to 0 eventually. So it's important to understand these two different types when it comes to stability of systems, and particularly the internal stability, because internal stability only has to do with the matrix A, right? So the only thing here, what matters is the poles of the open loop system. Now, so what are the criteria for the stability or internal stability of systems? So let's say the criterion for internal stability so a system is marginally stable if A has no eigenvalue in the right half plane, and all eigenvalues on the imaginary axis are simple roots of the minimal polynomial of A. So on the imaginary axis are simple roots. There's a few keywords here that I'm going to explain. One is the minimal polynomial of A. So that means basically, you know, if you create a characteristic polynomial, the most simplified polynomial is what we are looking for. That can describe A, meaning it includes all the eigenvalues of or poles of the system. And then there's this mention of simple roots. So simple meaning that they are not co-located, right? So not or have multiplicity 1. I can maybe explain this with an illustration here. So if this is the real and imaginary axis, right, in the two cases, then let's say you have roots in conjugate pairs on the imaginary axis. So these are simple roots. But if you have two roots at the same location, so let's say you have one here, one here. So if you have four roots which are co-located, that's not a simple root. So two roots at the same location. Okay, so important to note is the fact that eigenvalues, or in other words, the roots of the characteristic polynomial, they are in conjugate pairs if the characteristic polynomial has real coefficients. So these are in conjugate pairs. So if the coefficients of the polynomial are real constants. So maybe I can give you an example. So if if the polynomial is, for example, ax squared plus bx plus c, where a, b, and c are real numbers, then the roots will always be in complex conjugate pairs. Okay, so first condition was about marginally stable, and the second statement, maybe let me go back. So marginally stable if the condition is that if no eigenvalue in the right half plane, and if there's anything on the imaginary axis, that has to be a simple root. Otherwise, the system does not remain marginally stable. All right, the other type of stability was the asymptotic stability. So it is asymptotically stable if all the eigenvalues of A are in the open left half plane. Right, so that means the negative real parts so it means the negative real parts for all eigenvalues. Okay, that was the first type of stability related to the internal system stability, and as we said, it depends mainly on the zero input response. Now let's talk briefly about the external stability of the system. Internal stability is there even when we haven't really provided any input to the system. But the external stability relates to the behavior of the zero state response. Let's assume that the initial state is 0, and then we have to look at whether a bounded input result in a bounded output. Because we cannot expect a system to stay bounded if the input to the system is not bounded. So when it comes to external stability, we want to see whether a bounded input leads to a bounded output. And sometimes we also refer to this as BIBO stability. Okay, so let's quickly also look at the criterion for external stability. So to see if a system will be bounded input or bounded output stable, there are two options. One is if the impulse response, right? So if you look at the impulse response, because this impulse response is the one that is going to be convolved with the input signal. So if the impulse response is absolutely integrable, that means if you do 0 to infinity, absolute value of h of tau, d tau, if this is less than infinity, then whatever u is used as the input, you will get something which is bounded. The equivalent condition in terms of the poles is that if every pole of the transfer function has a negative real part, so if every pole of G of S has a negative real part, then you say that the system will be bounded input, bounded output stable. But there is a small caveat that you have to be very careful about, is a fact that we already saw earlier, but just to mention this again, that every pole of G of S is an eigenvalue of A, but not the converse. So, but an eigenvalue of A may not be may not be a pole. Right? And the reason why this can happen is because, remember, there can be a pole zero cancellation. So when we look at transfer functions, maybe there's also a zero exactly placed at the same point, so which might cancel the pole away, and hence, a pole may be missing, but the eigenvalue is still there. So I mean, when we talk about the external stability, then the important thing to consider is the pole of the transfer function, not the eigenvalue. All right, so that's the end of our previous discussions, and we will move to our new topic for this lecture. Does anybody have questions at this point before I move on? So our topic today is a different form of a controller for state space systems, and it's a slightly more advanced than state feedback controllers and dynamic output feedback controllers that we have seen in our lectures earlier. But it is interesting in several ways. One is that it has some design criteria for controller design. So this controller is called a linear quadratic regulator. We sometimes also refer this to as the LQR controller. And in a moment, we will see what the importance of an LQR controller is. So previously, we have really discussed feedback controllers. And the primary goal of such feedback controller is to alter the system poles, and in that it alters the system behavior. So previously discussed feedback controller were primarily used to alter the system poles or position them in some desired locations, and these locations are determined by some design requirements, right? So we have some design specifications, or we require a certain form of behavior of the system. So we try to position the poles accordingly. That's the primary goal of feedback controllers. And what we did was we simply designed the constant gain vector k. So some constant gains k. And we used it in the form of u equals to minus kx. So I'm sure everybody by now is familiar with what is such a feedback controller. So we use this to position the system poles anywhere. So more graphically, what is happening is you have you have a system with a certain pole zero configuration, and you can do different design choices. So one possibility is if the poles are here and here, then maybe let's call them the original poles. So you can shift them wherever you want. You can shift them here. And this is like choice one for pole locations. So if this is the kind of pole locations you choose, the feedback system will be stable. It will have a slow response, but it will also have some oscillations because of the conjugate pairs. So we have a conjugate pair of poles, which result in some oscillatory behavior, but we also have some negative real parts, which are going to kind of decay the system. So we may have a response, which is something like this, right? So this is how x of t may evolve as time goes on. But if we choose a different set of poles or set of locations to position these poles, then we will have a different behavior. And if I just draw you a rough estimate for the choice 2 for pole locations, then if you look at the same x of t, it may have some oscillations, but it may die out very quickly. Okay, so same system, different behaviors, and both of these can be done with just a simple choice of constant gains k. Okay, now, so what is the trade-off here? I mean, why would we do one as opposed to the other? Well, one thing is very clear, so your design choices inform the selection of pole locations, but also there may be some physical constraints. So for example, in the second choice of pole locations, the controller gains may actually be very high. So what that means is you will have to spend a lot of energy to shift those poles to that certain location. So such gains may actually get very difficult to realize. So even though theoretically you can position your poles to any location you want within the complex plane, but when it comes to practical selection of the gain vector, you may be constrained by some physical limitations. For example, energy constraints. And the other thing is you may also have instabilities. So and also lead to instabilities in the case of errors. If you have very high gains in the system, let's say the gain values are in thousands or millions, then a small error in the system states may, may make the system unstable. So you don't have to, make the gains kind of totally out of bounds. So that's where an LQR controller comes to your help. So in LQR controller is slightly different in the sense that you don't have to pick pole locations by yourself. Instead, you specify your some performance characteristics that you want your controller to have. For example, energy consumption, for example, how much time it takes to reach the stable or equilibrium state. So in an LQR controller, what is different is we do not pick pole locations. But obviously, it may not be very obvious. How do we determine where to put the poles? So instead, we find an optimal gain vector. So it's kind of an optimal controller, meaning that it is trying to minimize some objective functions. So the optimal K is picked by choosing some desired performance characteristics. And what do I mean by performance here is two different factors. So the first factor is how well the system performs. So that means how quickly you reach the stable or equilibrium state. So how well the system performs is actually related to the timing. So the second criterion or performance characteristics is how much effort it takes to achieve such a performance. So two things, how the system performs, and the second is how much effort is needed to achieve that performance. So you want to kind of balance these two things. Obviously, you can have a system that performs excellent, but that may take a lot of energy or a lot of effort for the controller. But on the other hand, if the system performs poorly, that may require much less effort. So you have to find that right balance. And if you're able to specify what the needs are in terms of performance and effort, then the LQR will give you an optimized controller. So to further motivate or help you understand what does it mean by selecting the performance characteristics, let's do a quick example. So I'm going to do a motivating example here. So example says, let's say you are commuting from your home to the workplace, right? So that's your home, and you want to make this commute, but obviously there's many options. So the question is, what would be the optimal mode of transportation? So we have a few options here. So for example, you can make a small table telling you the different options and the different characteristics or performance of taking that option. So, so let's try to do so let's try to specify two things. One is the time taken per trip, and we can also give it some weights. Let's call that weight to be Q. And the other important factor is the money, right? Or the cost that is incurred per trip. Okay, so then let's say J is the total cost. Okay, so the weights for the amount of money per trip is let's say a constant R. So I'm just going to say these are generically weighting factors. So let's say the first option is you choose a car to commute to the workplace. You can also have an option to use a bike, or you take a bus to your workplace, or you can also use a helicopter or a air taxi. Right, so maybe I will say you use an air taxi to go to the. So just hypothetically some options for you to commute. Now, let's say the car will take you 20 minutes drive. If you bike, then it takes you 75 minutes. Take the bus, maybe it's something like 30 minutes. And if you take a air taxi, you may come here in 4 minutes. And let's now, for now, let's just say the weighting factors are 1. So all are equally weighted. Now the cost per trip is also something important. So let's say if you take a car, you spend like $7. If you bike, you actually just use your legs, so you don't spend any money. If you take the bus, let's say you spend $2. And if you use an air taxi, you just use $400. Okay, and again, let's use the weights to be 1 for all these options. Now, if you compute the cost, the total cost, that's the weight multiplied by the time per trip. And so you have to multiply this and then add this times this. Okay, so if you do this, then it comes up to be $27, not dollar. I mean, it's a combination of the two values. One is in minutes, the other is in dollars. So eventually the cost function evaluates 27 here, values to 75 here, 32, and a 404. right? So, I mean, if you consider all these three options, it seems like most optimal way to commute is here, right? So if Q and R, yeah, sorry. So car is the best way. Thank you for pointing out. So it seems like this is the best way to commute, right? But this is an optimization. This is an optimization, right? So you're trying to weight different different preferences. One is the time, the other is the trip. So your J is really Q times time plus R times the cost. So Q tells you how important you value the time it takes to go, and the R is the value you pay to the money. So let me just go to the next page and say some comments. So if Q is high, so then we penalize the option that takes more time. The option so similarly, if R is high, we discount or penalize the option which takes more money. So the weights will decide what is the best option for you to pick. So now let's do two sub examples. So let's say if time is really important, right? So let's say you have very little time left to reach your workplace. Again, you have the same structure of Q and the R constants. So car, bike, bus. So now let's say the Q is very high, right? So 30. Then these values are the same. These are the characteristic of the options that you have. So what we change here is only the possible weights. And let's say R is again 1 because we are we think the time is really important for us. So if you compute the cost now, it's going to be 627, 2250, 932, and a 520, right? So now if you look at here, then basically it's best to use an air taxi. The time is really the important factor. On the other hand, if money is important, then what will happen is you will have a different selection. Just giving you the a numerical example to help illustrate the idea, but I hope the concept is clear. So let's say Q is all 1. Okay, I'm having some trouble here. So if I just copy down the same example, but this time making sure that the R is given higher value, let's say it is 40, and meaning that the cost is 40 times more important than the time it takes. So you don't really worry how much time it takes, but you really want to make sure that gives you the least cost. So if you try this option, your eventual cost is going to be 300 here. It's going to be 0 here. Oh, 75, right? So it's 75 here, 110, and a 16,000. Right, so it's very clear that obviously to save cost, you are going to pick the bike option to commute to work. So if I ask you which option is optimal, well, there is no answer to this. The answer is it depends. It depends on what? It depends on your preferences. So it depends on how much importance you you have for different performance characteristics. So for example, a prime minister, right? So prime minister's optimal choice may be an air taxi and a student's optimal choice may be to do the bike. Right, so the answer is it depends on what are the preferences. But one thing is clear, that all these all the selections are optimal. When I say optimal, in terms of the cost function. In terms of the cost J, whichever option you pick is actually the optimal option. Only thing that different is the preferences. So, okay, I mean, I hope you get the intuition behind selecting the best option to do something. So let's get back to the control system scenario and try to develop a control strategy that takes into account the different preferences on time and money, or time and effort. So if we come back to the control, oops. scenario, again, x dot is ax plus bu. We can set up a cost function that takes into account these two the preferences. So that takes into account our preferences on time and effort. And again, there are many choices when it comes to selecting cost functions, but one of the cost functions that we can pick is a linear quadratic cost function. Okay, so let's see what that linear quadratic function looks like. If I pick j as the integral from 0 to infinity x of t transpose q x of t plus u of t transpose times matrix R times u of the u here. So remember, these are quadratic forms. So if you have a vector x, then x transpose ax is a scalar, right? So if you have 1 cross n, then n cross n, and then n cross 1, that's a scalar, and it's also called a quadratic form of the matrix A. So, I mean, here we have the state vector x and the input vector u. So if you create quadratic forms using these two vectors, what you will get is a quadratic cost function, but it's eventually a scalar value. It's quadratic in terms of the x and the u, but if you evaluate this, it turns out to be a scalar. So if you do this dt over 0 to infinity, then, and where u is minus kx, then the goal is to find out the k, which minimizes this cost function. If you found that k, then that's the best controller without specifying what is the location of poles. So I mean, here the Q signifies the performance, weights, and the R signifies the effort, weights. Right, so the higher the Q values are, the more we want to make sure that the state vector does not go far from 0. And the higher the R values are, the smaller the input vector will be. So meaning that minimum energy is spent on the control. So if I want to try to measure what the performance measure is, let's say you have the time axis and you have x of t, then let's say you have two different options. One is that your system behaves like this, and the other is that your system behaves like this. So which one is better in terms of performance? So performance actually means how much time it takes to reach the equilibrium. So in the case of the blue line here, you actually reach zero in a much smaller time than as compared to the black line. And also, while reaching the equilibrium, you're also spending less energy. Energy is coming from the area under the graph. Right, so this signifies a good performance. While the black curve highlights a poor performance. And there's also another option that could have been possible, but that's not a good measure of the performance, because the area starts getting negative, and hence, it's not the right measure to judge how well the system performs. So this is not for performance evaluation. So that's why we are using a quadratic function to measure the cost of control. So this quadratic form is always going to be positive, first of all. And the way it is designed, it will depend on what are the weights of Q and R in the optimization. So interestingly, in the way this LQR controller problem is posed, one of the interesting factors is that the matrices Q and R, they are in a diagonal structure. So they generally have the diagonal structure. So if that's the case, then X transpose QX is going to be something like this: X1, X2, Xn times Q1, Qn. The rest are all 0. So X transpose Q and X will be X1, X2, Xn. So if you compute this, that's going to be in the form of a quadratic function. You will have Q1 X1 squared plus Q2 X2 squared plus so on, Qn Xn squared. So therefore, you see that Q1, Q2, Qn are weights for the individual states. X1, X2, and Xn. So similarly, U transpose RU is having a similar structure. So you have U1, U2, Un, and then you have a diagonal matrix with R1, R2, Rn. Well, maybe it's Rm, not N here. So let's use a M here. The off diagonal elements are 0. So if you kind of multiply this together, then it will be R1 squared, U1 squared, R1, U1 squared, plus R2, U2 squared, plus Rm um squared. So again, the R1, R2, Rm are individual or weights for individual inputs. Or individual inputs U1, U2, M. So in most cases, of diagonal terms of Q and R, they are 0. However, they don't have to be. Okay. You can also consider the matrix form of this formulation. So if you have X transpose, U transpose, and Q 0, 0, R, and then X and U augmented together, what you get is a X transpose QX plus U transpose RU. So again, that's the same cost function that we saw in the formulation of the LQR objective function. Now, just a small note here, which is also important. So note, if off-diagonal terms are non-zero, for example, it's going to be Q here, and then R here, and then N here, and N transpose here, and then N matrix penalizes the cross terms. So that is like X transpose U and U transpose X. So those type of terms. So the cost, so the general form of the cost function will be the following. Will be J is the integral 0 to infinity X transpose QX plus a U transpose. So U transpose RU plus 2 X transpose NU dt. So that's the general form of a linear quadratic cost function. And in most cases, we just assume that N is 0, meaning there is no penalty for cross terms. And we are just trying to balance between performance and energy consumption. So we just pick the Q and the R appropriately, and then let the optimizer get you the best possible selection for the gain vector K. Okay, so now let's do the solution to the LQR optimization problem. right? So what is the LQR? Optimization problem. So we are trying to minimize the function j, which is equals to some t to tf, right? Obviously, we cannot consider a so I mean we can consider a finite horizon LQR, because an infinite horizon will require an optimization where the integral is 0 to infinity. So I mean, obviously that's also possible to do, but requires some additional. So we will just consider finite horizon case. So we transform the LQR problem as t to tf x transpose of t times q times x of t plus u transpose of t r and then u of t dt. That's your objective function. You want to minimize this, but you also have the constraints that x dot of t is some ax of t plus b u of t, and your y of t is some c times x of t, and your u is minus k of t x of t. So that's the three constraints you have. Right, so you want to minimize cost function, but you know that your x evolves with time according to some dynamics, and your output y is some function of c, and your input has to be coming from a feedback controller, right? So there's minus kx sitting somewhere. So if you combine these two informations, then, or these two constraints, what you're saying is that x dot is a minus b k x, right? So that's the constraint we have, though there's no more u sitting there, and we can also replace the u as minus k here. Now, so this is general form, but if you, so I mean, in this case, if tf is less than infinity, then the problem is called a finite horizon it's a finite horizon LQR problem, and if TF is infinity, then the problem is called an infinite horizon LQR problem. Okay, so both can be dealt with, but they have different solution methodologies. So I mean, most likely we will confine ourselves to the finite horizon LQR problems, because it is simpler than the infinite horizon. Now, in this LQR problem, where the objective is to minimize the cost function and constraints are coming from the constraints are coming from the LTI system, the only question is how do we pick the matrices Q and R? So as long as we know what the Q and R is, what we have to do is to find the K that minimizes that or that solves the optimization problem. To pick matrices Q and R. Right, so I mean, I'm just going to put a few comments here. One is that there is no definitive answer. There's no fixed way to do it, but it is more but it's more intuitive, right? And then figuring out where to place the poles. The matrices Q and R are in a relative terms. So you so if Q is 2 times the R, means that you put twice the emphasis on Q than R. So the general process is to begin with Q equals to R equals to identity n cross n, and then you can tweak them or modify them iteratively until desired results are achieved. Okay, so that was a quick note, a quick detour. Now back to the solution of the LQR problem. As a refresher, LQR problem is trying to introduce matrices Q and R that signify how much time and energy is spent on achieving the equilibrium, and we want to minimize the gain vector K, or we want to find a optimal gain vector K that minimizes the cost, given that a certain set of constraints are there coming from the control aspects. So the closed loop feedback system, so closed loop feedback system can be written as x dot equals a minus bk times x, which can also be written as x dot is a controllable x or ACX not controllable. So for this system, the X at time tau is given as the product of phi c tau t times x of t. So which means that x, or the state at time tau, depends on the state at time t, and the relation here is something called a transition matrix, e to the at, right? Remember e to the at. So that's coming from the transition matrix, and this is by definition the idea behind transition matrix, because you can transition from time t to time tau using this very simple relationship. So, I mean, if that's the x at time tau, then we can modify our cost function accordingly. So let's consider the cost function. So you consider V as the T to TF X transpose tau QX tau plus the U transpose tau times R times U tau, and then D tau. This is just a replacement of T with the tau because that they are dummy variables. So so U, so we can write this as T to TF. Instead of U, we are going to put minus KX. So let's say this will be X transpose tau, Q X tau. And then we'll say this will be a minus, right? This is so I mean the minus will go away with the plus because there's two U's. Yes, right. So so U transpose will be KX transpose, right? So basically the X X comes first, right? It will be X transpose tau, K transpose tau, and then R, and then U is KX. So K transpose tau. Oh no, not transpose, right? So KX, right? So now we are at this place. I mean, from here we can see that the X transpose and this one can be brought outside to just say T to TF X transpose tau. It will be Q plus K transpose tau RK, and outside you will have X of tau. I'm simply taking out that X and X transpose outside the braces. Now, so we said X at time tau is actually phi times XT. All right, so remember this. So it's the transition matrix times X of t. That leads to X at time tau. So this thing here will be the transpose. So you will have X transpose t phi C transpose theta. So you have T, TF, and two of these. So X transpose D, phi C transpose D tau. Inside you have Q plus KT, R, K, and then phi T tau X of T. And outside you are still in the tau. So let's call all of this I'm going to do one more. So let's call X transpose T, because this is a constant, right? The T is not the variable of integration. So we can bring this out. So we are left with the phi Q plus K R K tau phi C T tau and X of T. Right, so all of this in the middle, we can call this as M T comma TF. So our short form for this will be X transpose T times M to TF times X of T. So this objective function V can be written as X transpose M times X. So, I mean, the good thing is we have converted that objective function into a quadratic form. And next we will use our optimization or derivative methods to optimize or minimize the V function. So V I have expressed as X MTTF and then XT. Now our goal is to minimize V. So we take its time derivative. Right, so we take dV by dt. So it's going to be d over dt of this X transpose T MTTF X of T. Right, and so these are three functions. So what we can do is consider this separately and then this two separately. We need to do a product rule. So when we take a derivative of the product, what we do is we keep the first as it is, and then take the derivative of the second function. Right, so we take a d over dt MTTF X of T, and then we keep MTTF, and then we have d over dt X transpose of T. Okay, so that's the derivative, and then we need to equate it to 0. But let's simplify this first. So, so I'm going to call this as XT T. And again, this is another product. So I will say this is going to be M dot times X of T plus M TTF times X dot T. Right, and then we have M T TF XT X dot T transpose. Oh, I think there's a error in the matrix. So these are not scalars. So I think we should be careful. I mean, here we cannot reverse the order. So this will always come first, d over dt. And then mt tf xt. So it was x. It's x dot transpose t, and then m tf, and then xt. Okay. So next we can expand this. So so therefore the dv over dt is, let's say, x transpose t okay, so okay, yeah. Before we get there, let's say that from the dynamical model, this thing here is x dot, right? So x dot is what? AC times xt. X dot is ax, right? So I mean a minus bkx. And here this is going to be x transpose t AC transpose. So what we are left with is x transpose t AC transpose MTTF xt plus x transpose t, and then there's m dot DTF xt. Maybe we can keep the xt outside. So m dot plus okay, have I missed something?
It's up
What is it?
into AC. It's up.
With the m dot?
No.
Which,
Oh,
which one?
here it should be m dot in the first term.
Yeah,
The second term it should be m.
m.
Yeah.
Okay, so it's m and then x. Oh, AC, right? Oh, okay. So and then x is outside, right? Okay, so this can be actually combined, right? So xt here we can say it is AC transpose MTTF plus m dot plus m AC and then x of t outside. So that's your dv by dt. So let's call this equation 1. Okay, so this is one equation. Now for the second equation, we can look at it from the other perspective. So on the other hand, your V, which is T to TF, X transpose tau, Q plus K transpose RK, X of tau, B tau, right? So if you just put u equals to kx, this is something you will get. So let's call all of this as L. So what we get is V is T to TF, X transpose tau, L, X of tau, D tau. So from here, if you try to compute dV over dt, that's pretty simple. I mean, you require a Leibniz integral rule. I mean, I'm not going to mention it here, but if you use the Leibniz integral rule, what it says is you take the derivative of the upper limit, which is 0 in this case, and then you minus derivative of the lower limit, which is 1. And then you move the derivative inside. So no, and then you substitute the lower limit inside the function. So it's X transpose T and LT and XT. So that's the dV by dt using the other way. So this is equation 2. So now comparing one and 2, what we get is basically minus L will be equals to AC transpose M GTF plus M dot GTF plus M TTF AC of T. So rearranging results in the following. So you have minus M dot GTF equals M GTF AC plus AC of T. I think there's a transpose somewhere. So AC transpose M ETF plus L. Okay, great. So this is a differential equation for M, right? So we need a boundary condition. So we also note that M TF is 0. That's the boundary condition we assume. Okay, so now if you expand this, so expanding the differential equation, by saying that AC is actually A minus BK, right? So what you will get is minus M dot is M times A minus BK plus A transpose minus K transpose B transpose times M plus Q plus K transpose RK which is L, right? This was L. So, so our goal is find M hat such that V hat, which is X transpose M hat X, is less than X transpose MX for all X and M. That's the minimizer. So this, if that happens, then this optimal M. So now the question is, how do we find the optimal K vector? So first we have to assume that there exists an optimal K hat. That minimizes M hat. Okay, so if that's the case, then now we will find a differential equation satisfied by M. M hat. So there is still some rigor involved in the proof, but eventually we will result in a easy to understand, easy to follow solution for the LQR controller, but just the intermediate steps are a little tedious. So let's consider the following decomposition. So M is M hat plus N, and K is K hat plus Z. Right, and we are assuming this is optimal M, and this is optimal K. So I mean, that's an assumption. So we start off with this, and so consider the following set of equations. So one is minus M hat, M dot is M A minus BK plus A transpose minus K transpose B transpose M plus Q plus K transpose RK. And you consider the other example, other equation where we have M hat. M hat is considered the optimal M, and the K is considered, K hat is considered the optimal optimal K. So A transpose minus K hat transpose B transpose M hat plus Q plus K hat transpose R and K hat. So if we subtract these equations, then what we get is, so remember M hat was considered to be M plus N, right? So just assuming M is M hat, so M hat is, so that's not this one. M is this one here. So this M is M hat plus N, and the K is K hat plus Z. Right, so if we subtract them, we will get some error, dynamics error, differential equation. So we will get minus N dot is N AC plus AC transpose N plus K hat transpose R minus M hat BZ plus Z transpose R K hat minus B transpose M hat plus Z transpose RZ. Right, and here we can just let's call it L tilde, all of this. Right, so we get minus N dot is NAC plus AC transpose N plus L tilde. So comparing with minus M dot is MAC plus AC transpose M plus L. We can say that MTTF is the T to TF of phi C L tau phi C T T tau, oops, T to tau D tau. So N will be, I mean, just as a comparison, you will have some phi TTF, and here you will have L tilde. Okay, so now because we have been able to express the difference in the similar form as the original differential, as the original integral equation, except the fact that the L is now replaced by L tilde. So we have to make an argument here that justifies that M hat is actually the minimum. So V, since V hat is the minimum cost, then V hat, which is X transpose M hat, X has to be less than X transpose M hat plus N X, right? And this here is equals to X transpose M M hat X plus X transpose N X, or equivalently X transpose NX is greater than 0, or N is a positive semi-definite matrix. Okay, so at least the matrix N can be proved to be positive semi-definite, and that was the proof for that. Now notice L tilde is K hat transpose R minus M at B Z plus Z transpose R K hat minus B transpose M hat plus Z transpose R Z so since Z is arbitrary, so so the minimum occurs when this piece here is 0, right? So if you want to minimize the L, Z can be picked whatever value, right? So we don't have control over Z. We can only change the optimal K hat. So the best we could do is try to make this factor 0. So if you try to do this, then R K hat minus B transpose M hat is 0. So what we eventually get is your K hat is R inverse B transpose M hat. So therefore, the optimal solution to the LQR problem can be written as K hat equals R inverse B transpose M hat. Okay, so still interestingly, there is M hat. So M hat is the solution to the differential Riccati equation. So what is that equation? That equation we have seen already. So it's minus M hat equals M hat A plus A transpose M hat minus M hat B R inverse B transpose M hat plus Q. So I haven't given you the yeah, so I think we have seen this, the exact same form. And this thing here is called the differential Riccati equation, or DRE, with boundary condition saying that MTTF is actually 0. So so final word is to design an LQR controller given the Q and R matrices, we need to solve the Riccati equation for M hat, and then use it to find the optimal controller gain K of K hat, which is equals to R inverse V transpose M hat. So how to solve the Riccati equation is the topic for the next lecture. But let me go back quickly and run you again through all these computations that we did. I think it was really a tedious process. So maybe some of you might not have followed it properly. So let's try to go over this quickly. So basically, we had a cost function in terms of the Q and R matrices, and we came up with this cost function V as the combination of two different quadratic terms. One is in Q and the other is in R. One signifies the performance or the time taken for the system states to settle down to zero. The other considers the amount of energy spent on the control. So if considering that feedback controller U equal to minus KX, we end up saying that the cost function can be written as X transpose times M times X. So so once we had that cost function, we wanted to make sure that we minimize the cost. So we took the derivative approach. We took the derivative of the cost function with respect to time, and we ended up in the expression one. So we have X on the outside, X transpose, and X on the extreme right side. Inside, we have something A times M plus M dot plus M times A. So this derivative can also be written as minus X transpose times L times X, using another formulation where we do not, where we take the derivative directly. In the previous example or previous method, what we did was we went to the transition matrix, did the expansion, and then took the derivative. But if we take the derivative directly, then that's what we get. So eventually we want to find a closure. So we equate these two and come up with a equation that is called a differential Riccati equation. And remember, to find the optimal gain, we have to equate this to zero. So basically that's where an optimal M hat can be obtained. Now, the important thing is this equation does not involve a K. So we had to do a further processing, because eventual goal is to find the gain vector K. So even if we solve this equation, we are going to find M, which is a matrix. This is a differential equation in M, and in the next lecture, we will see how such a differential equation can be solved. So let's say we are able to find the optimal M that minimizes this cost function. Then the next step is, how do we translate that to K? So instead of AC, we substitute the K in there, and now we are left with optimizing the M and K together. So So one way is to do a using the error-based approach. So we consider M and K are slightly displaced from the optimal. Right? So we find the two equations, one with the optimal values, the other with a slightly displaced version. And the displacements are arbitrary. And then we compute the error dynamics. So when we subtract these two equations, we get to the error equation. Error equation is expressed in a similar form. And now the goal is how do we minimize the error, right? So minimum error can only be done when all of these terms are minimized. So what we can change here is the L, because L depends on the K. So realizing that to make sure the difference between optimal and the displaced version is minimum, we try to minimize the L, and by looking at the expression, the best thing we could do is to make this 0. So automatically the first term, because this is a transposed version. So there's a K and R and M and a B, but just a transposed version. So if this second term is 0, this is again 0. And the final thing, we don't have much control because Z is an arbitrary thing. So the minimum that we can achieve is when this term can go to 0. So that is where we find a relationship between K and M at the optimal values. So our LQR controller can be summarized in the form of this elegant expression saying that the gain vector K that minimizes the cost is R inverse B transpose M hat. And M hat is a solution to the differential Riccati equation. So there's still some doing before we understand how to find the controller. But the whole purpose of doing all that complex mathematics is to end up into this simple expression for the LQR controller. Next lecture, we will see some numerical examples, some solution methodologies for solving differential Riccati equations and finding LQR controllers. But that would be it for today. And if you have questions, let me know. Is that clear to everybody? Okay. So this week, you will have a quiz instead of the homework. And I've already said in the beginning that the project mid-review is coming up. So end of this month, 31st of March, you are required to submit a half-baked version of your project report just to make sure that we are going on track and you are not lagging behind in your progress as well as your performance. So try to submit that mid-review. Hopefully I'll try to get back to you with feedback wherever it's needed. And
Professor, will the quiz cover the material from today?
yes, today and maybe the previous lecture. So kind of combined stuff. But I don't think we have done a lot of numerics or numerical examples. Probably the MIMO controllers are a bit hard to do, at least from the quiz standpoint. So quiz is mainly is a factual information, right? So for example, what is the difference between LQR controller and a state feedback controller. So, you know, you don't have to specify the location of poles. Those depend on performance characteristics and so on. So these type of factual information are important for quiz purposes. I don't expect you to do a lot of computations. Even in the previous quizzes, I think there were smarter ways to figure out the numbers quickly. You don't have to do, like in most cases, things were already in canonical forms. So you could just look at them, compare it, and find the answer directly. All right, so any other? Yeah, I was mentioning that your final exam week is the week of 22nd to onwards, 22nd to 29th. So 28th is going to be your final project submission. And before that, on 22nd of April, there will be a project presentation. So you have two options. One is to do a in-class presentation. You could either come to the class or you could do it via Zoom. It's a 10-minute presentation providing details on your project. I don't know if I need to explain to you the requirements, but it's pretty much like any technical presentation where you provide an overview of the project that you have done, what is the methodology used, what's the results are, and you know, standard stuff. What's the conclusion and so on, what's the future directions. But you could also choose to do a recorded presentation. So if you choose that route, then you have to send a recorded video presentation to me. That's going to count to your final project. And after this course presentation, the only thing is the project submission. So you still will have like a week to finalize your reports and submit them. Okay, so I think multiple opportunities for you to get feedback. I think mid-review is going to be a good opportunity then based on feedback and questions from your peers during the presentation. I think you can still improve your reports and submit them. Okay, any other question before we disperse? Yeah.
Am I placement can we also use like the arguments formula in single?
No. So that's not possible. Ackermann's formula is for I'm sure there will be a version of Ackermann formula for MIMO placement, but we have not covered it in the course. So what we have seen is really comparison and doing it by comparison. Okay, so if you still have other questions, you feel free to send me an email and I'll get back to you as soon as I can. All right, then I hope to see you next week and you all have a wonderful week.
Thank you.
Bye-bye.
Thank you, Professor.